Hello, everybody. Thank you. My name is AMARACHI, IHEANACHO, and I will be speaking about a topic that I've been learning a lot about recently, which is event-driven architecture with Go and Kafka. So yeah, to start off with, I think I need to explain why event-driven architecture is even important in the first place, because I feel like we keep learning and learning a lot of stuff, so we don't get overwhelmed. I think throughout these entire sessions, I guess we've discussed in some ways the dangers of like strictly monolithic applications, because they are so tightly coupled, it becomes harder to scale. For example, if a feature of your application is doing extremely well, and you want to scale that feature, because it's so tightly coupled, you end up scaling the entire application. Two, if something is wrong with a particular feature, the entire application kind of goes down with it, right? Also, because you're scaling inefficiently, you're using a lot more resources than you should use, you have scalability issues, you have problems with time and everything. And that's why I think microservices is gaining so much attention, because microservices split monolithic applications into smaller, independent, or slightly independent services that can communicate with each other. And EDA takes that loose coupling to the next level. EDA, which is event-driven architecture, uses events to communicate between the coupled services. So what that means is that, okay, if a user does something that changes the state in an application, okay, a user adds an item to a cart, a user processes a payment or tries to pay with their card, an event is raised up. So it's like, oh, look at what this user is doing, check this out. And that's basically what event-driven architecture is. It uses an event to tell different services in your application what has happened in your application. And this is great for many reasons, because one, scalability and flexibility. The perks of loosely coupled application is that you can scale whenever you like. It's very flexible, it's loosely coupled. Because when one service goes down, the rest does not go down with it. It's highly fault tolerant, it's resilient. Event sourcing and auditing, which I would go into details more. It's asynchronous, it's secure, and it's private. So what is an event? An event is raised when there's a change in state in your application. They contain just cold hard facts of what is happening in your application, and they're a lot like logs in the fact that they are immutable. You can't update an event when it's raised. You can't delete an event. And it tells us a lot about what is happening in your system. A user added something to their cart. A user took away something in their cart. A user tried to make payments. A user canceled the payments. When all these things are happening and they are changing states in your application, events are being raised, and which is why I talked about event sourcing originally. By the time you put together all these events that has been raised because of changes in state in your application, ideally, you should be able to tell the current state of your application when you do the plus, the minus. You should also be able to tell the state of your application about 2 weeks ago, because events are immutable. You can't change them, you can't edit them, you can't delete them. Of course, you can clean them up when you use tools like Kafka, which I will get into. So this is an example of what an event would look like. Of course, you are in charge of defining the structure and whatnot. So this is an event type. An item was added to the cart, the timestamp, the user ID, the item ID, how many quantities of a wireless mouse did a user add to their cart, the price, and whatnot. So EDA are made up of 3 important parts: the producer, the consumer, and the broker. The producer, like its name would suggest, are the ones in charge of creating that event or like publishing that event. Okay, an architect, a user, like I always say, added something to their cart. Then you get an event, okay, this user did this. The architecture that is publishing that event is the producer. The consumer then receives this event and figure out what they want to do exactly with this event. Do they want to process it? Do they want to send an alert or a notification that, oh, somebody added something to their cart, do they want to change the inventory and be like, okay, because somebody added something to their cart or because somebody paid for something, this is how many like wireless mouses we have. Then you have the brokers. The brokers are the middleman that are in charge of the communication between the producer and the consumers. The main reasons why we care about EDA in the first place is because of loose coupling, one of the reasons. So it would not make a lot of sense to then directly attach your producers to the consumers and be like, okay, a producer cannot publish an event if the consumer is not available or this. So that's why you have the middleman. The middleman collects these events that have been published. They kind of store it and they kind of notify like consumers that, okay, this event is happening and you mentioned before that you're interested in this event. So you can then retrieve this event and process and respond to the events as you would like. Great. So this is kind of like a picture. You can have multiple producers, you can have multiple consumers, which I guess makes sense because when you have an application, especially a very complex application, too many services are going to be raising up events. Like, it's not just, okay, this user added an item to the cart. We're going to wait for another user to add an item. Too many services are producing events, so you can have multiple producers. Then too many users are going to be subscribed to that event. For example, now if you're using Netflix and you press play on a video and an event is raised, there are different services that will be interested in that. One, the playback service that would play that event. The service that is responsible for updating your watch list, updating your history will be interested in that event. The service that is responsible for recommending more series like that would also be interested in that event, and those could be like separate services. And because they are all interested in an event that the producer or the multiple producers are creating, then you have multiple consumers. Then this middle person is the event broker. And that's basically what Kafka does. So Kafka is basically the middleman, the person that makes all this happen, the magic man, basically. So it's used to publish, store, process, and subscribe to streams of events or messages in real time, like I kind of explained before. With Kafka, microservices can publish events, microservices can subscribe to those events. Kafka can store those events for a particular time that you've stated so that you can retrieve it later. So for example now, if you are using a producer and the consumer is not available to process those events, Kafka is not going to delete it. The producer too also does not really care if the consumer is there. What the producer's own thing is that, okay, I am producing, this is what is happening. I'm notifying other applications that are interested in this. I'm going about my day. So Kafka can store that for later retrieval. Kafka can replay events. Kafka can transform or process events. So Kafka are made of like core components. You have topic, partition, offset, zookeeper. A topic basically categorizes a bunch of events in a, I guess, topic. So if you have events that are related to payment, events that are related to inventory, events that are related to playing videos or whatnot, they are usually categorized under a single topic. You are the one that will say what the topic name is. You are the one that will specify what the consumer that are interested in those topics. So the topic is basically a category of events on a particular topic. So you have partition. So the topics are further separated into different partitions. And one thing about Kafka is that you can have multiple brokers. So, and this can help with fault tolerance in case a broker goes down. You don't be like, oh, what's happening? You can have multiple brokers. Also, if you want to, if too many consumers want to consume events at the same time, because you have multiple brokers, it's easier to do that. And partition is so cool in the fact that it separates these topics on different brokers. So one, as a user, you can read and write to different partitions on the same topic at the exact same time. So partitions helps with scalability. Secondly, because partitions are separated on different brokers and you can also replicate partitions, they also help with fault tolerance. So if your broker goes down, because the data in that broker is replicated on different partitions which have been distributed on different brokers, you do not lose that data. It's okay, I'll get into how Kafka replicates this data. So you have offset. Because partitions are storing messages or events, each of those events have like a unique ID. So probably from 0, 1, 2, 3, 4. So you can understand how many of these events you have processed, how many you've not processed. And those unique ID are called offset. Then you have Zookeeper, which is used to manage and coordinate Kafka brokers. Like I said, you can have multiple brokers. You can have multiple brokers, topics, partitions, and you can replicate partitions on different brokers. When a broker goes down, you can use a different broker that has the replica of the data. You can also add a different broker just for scalability and fault tolerance, and Zookeeper helps with all of that. So you have a replication factor. A replication factor determines how many times you want to replicate a partition. So, of course, you would like to have multiple copies of a partition just for fault tolerance. So if you have a partition spread across many brokers, so you have broker 1 can have the leader. So the leader is the original data of the partition. So the data that is responsible for reading and writing. So that's the leader. The follower is just the replica. So if the broker that contains the leader of a partition goes down, you can, Kafka then promotes the follower, promotes the replica to be the leader. So you can then read and write to that follower. And that helps with fault tolerance. So this is like an image. You have the broker, you have the producer, you have the consumer groups. You have topics, which are groups of events. So topic 1, topic 2, topic 3. You have partitions. You also have 0, which is like the offset, which is the unique identifier of a message in a partition. So you can see a Kafka topic, you have partition 0, 1, 2. You have offset 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which represents the messages in a partition. You can have multiple producers, all of which are pushing messages to this Kafka cluster, which has multiple brokers. Then the consumers are pulling messages from that broker. You have multiple consumers. You have the Zookeeper, which is in charge of the brokers, the broker 1, broker 2, broker 3, and that's there. And so why is Kafka cool? Like I said before, Kafka helps with loose coupling. And because it allows loose coupling, it's easier for you to scale. If, for example, demand is getting higher and you need more producers, more consumers, you can easily just add that to your architecture. They are not so tightly coupled. You don't need, okay, dang, there's so much demand, let me scale my entire application. No, you can just add more producers or add more consumers, which leads me to my next point. You can have multiple producers and multiple consumers. You can define how long you want Kafka to hold your data for. It's highly performant because partitions are distributed on different brokers, and because partitions are distributed on different brokers, customers can retrieve data at the same time from different brokers. So you can retrieve data on the same topic from like broker 1, broker 2, broker 3 at the same time, because Kafka distributed the data in the partition on different brokers. It's highly available and fault tolerant because it replicates the data on different brokers. So if a broker goes down, you still have that data. It's secure. And the reason why it's so secure is because it's so loosely coupled. Services that do not require information on this do not need to have access to that information, unlike monolithic application where everybody's committing to the same repo. So different services will have access to information they should have not had access to in the first place. Also, Kafka has a larger user community. It has a growing user community. Kafka allows for multi-language environment. So you can use Java with Kafka. You can use Go with Kafka using the Sarama library. So yeah. So why Kafka and Go? Why should we care about using Kafka with Go? So first of all, Go allows concurrency modeling. So with concurrency, everybody knows that concurrency allows you to process different tasks at similarly same time. So when you are calling an event, or when you are producing an event, you don't need to wait for that event to be answered before you try to process another event, or before you try to create another event. And you can do that because of Go. Also, Go is very performant and has low latency. Go is simple, and Go is easy to maintain because it's strongly typed. Go has native support for networking and distributed system, and Go has a large community. So here's how you can implement Kafka. So I'm using a Docker image. For the Zookeeper, I'm using a Confluent Docker image. I'm exposing the port 2181. I put a time of 2000, and I expose those ports. Then for Kafka, I use the Confluent image. I say it depends on Zookeeper, which means that do not start Kafka if Zookeeper is not on. Then I put the ports and connect to the Zookeeper and specify a replication factor of 1. Of course, you can change that to whatever you'd like. Then you have the producer. I'm using the Sarama library for creating my producer and my events. I would like to say the documentation is easy to understand, but not really. So you have the Sarama new sync producer, and this producer collects the address to your broker, which, if you see here, was 29092. So you use a new sync producer. A new sync producer means that when we create an event, we have to wait until Kafka tells us that, oh, I have received your event, before we move on to the next line of code, or before we move on to the next event. If that doesn't work, close the producer. So we have a topic of test topic. We have a message. We create a message struct. Then we send this message, and we create a message, and we collect the partition and offset. So then it prints out, okay, the partition and offset. So this is usually what you'd get. So message sent to partition 0 with offset 1. Then on the consumer side, you have the new consumer object, which we get from the Sarama library. We pass in the address of the broker. And if that doesn't work, of course, close the consumer. We specify the topic that we want to collect the event from. And we pass in the topic. We also pass in Sarama offset orders, which means we want to collect all the messages from 0, like all the messages, all the events on the partition, consume the partition, and collect the partition consumer and error. If there is an error, close that up. So we create a channel, and this channel is going to collect operating system signals, which are just basically, if the user does Control-C or tries to close that channel, we should close it gracefully. So that's basically what that's about. Then we can be like, okay, receive the message, yada, yada, yada. Received message, then print out the message value. So this is what you would get. This is the message value that we sent originally. Hello, Kafka. Hello, Kafka. And the thing is, the consumer just keeps running. It's just waiting for you to send more like events. It's just listening for more events. So that's why you need to close it, and need to close it properly, so you can let go of any resources that it's currently using at this point. So you can see that it's not closed yet. So how many times I'm running it, I'm going to get, okay, received message, received message, received message. So what are the challenges of an event-driven architecture? I think with most things in life, as there are pros, there are cons. First of all, event-driven architecture are complex. So unless you really need event-driven architecture, unless, okay, you're struggling with scalability issues, or your system is so popular, maybe don't use event-driven architecture. Secondly, event ordering. So because the producer really does not care if the consumer processes the event or responds to that event, the producer is only like, okay, let me create the event and be on my way. There can be plenty of problems when that happens. So if, for example, a user tries to make a payment, then I was like, oh, no, I changed my mind, and cancels payment. And for whatever reason, the cancelled payment event reaches the consumer before the create payment event. The consumer will try to cancel a payment that never existed in the first place. So that can be an issue, especially when different consumers are creating the different events, different producers are creating different events, and a single consumer is consuming all the events. So event ordering can be a problem. Thirdly, debugging and monitoring. Because event-driven architectures are so complex and we have multiple producers producing an event and multiple consumers consuming an event, it becomes difficult for you to know what exactly is happening in your architecture. It becomes difficult to know, okay, who produced this event? Why did we consume it the way we did? And so debugging and monitoring becomes a lot more difficult. That's why you have to use all these distributed tracing tools like OpenTelemetry. OpenTelemetry allows you to collect metrics, logs, and traces from your architecture, so that can help you understand what exactly is going on, what caused this and what caused that. Also, AWS X-Ray, I know that they do like tracing. Also, ignoring event schema evolution. Like most things in life, your architecture will evolve. So if your architecture evolves and it starts sending events in a structure that your consumer is not equipped to handle, maybe has different values or different variables and everything, and your consumer is just not ready for that, that can be very problematic because your consumer will not know what to do with that event when that event has been raised. So the consumer will not even know how to process it, let alone respond to that event. So you need to make sure that if you are evolving or if you are changing your architecture, it's both backward and forward compatible. So any new consumer you add should be able to process that event, and old consumers should also be able to process that event. Also, forgetting about back pressure. The thing about events is that if, a user adds something to their cart, removes something to their cart, makes a payment, cancel payment, and an event is raised each time, you can start to overwhelm your consumers. So event-driven architectures are great for complex architectures or complex applications. So yeah, basically that's it. So you can connect with me on LinkedIn, on Twitter. I write articles sometimes on dev.to. So, yeah, I hope this was not boring and whatnot, but thank you for having me.